Any questions you have from what we have done till now?
Sir, I wanted to ask something.
Okay.
So last time we proved that 0 was less than 1, and in that we used that -1 into -1 is greater than 0.
Mhm.
I was not able to prove that. Like I did all the other exercises and I was able to do them. But
Can you repeat again what you just said?
so can you do the -1 times -1 is greater than 0 proof?
Okay, so let's do one thing. So this is the kind of things that the course page is for. Okay, so if you write there, maybe I can reply there. So we'll save a bit of time here.
Okay, sir.
Huh?
Yes, sir.
Okay, anything else? Okay, so where were we last time when we ended? I defined the notion of an inductive set. In R. So what was an inductive set? S is an inductive set if whenever something belongs to S, these two S's will cause a problem. So let me A. The successor x plus 1 that also belongs to A. So if you call a set inductive, this happens. And then we define the set of natural numbers to be the, what was the definition?
Intersection of all inductive subsets of R including A.
Right. So this is by definition intersection of all inductive subsets of R that contain 0. Okay. And we had already observed that intersection of a family of inductive sets is again inductive. So this itself is inductive, contains 0. These two you already can see from the definition. Okay, now the other observation that we can immediately make is the following. That this is contained in this subset. Why? Because this is an inductive subset of R and this contains 0. Right? So this is one of these sets over which we are taking intersection while forming this set. So this is going to be contained here. So what that tells you is in particular that any natural number is greater or equal to 0. Okay, so this is something that, I mean, we are all familiar with, but I'll just mention nevertheless. So the relation we had defined, I mean, we had on the set of real numbers is this, right? So we can talk about A being related to B. When we write the same thing, we'll also express by saying this. Okay, so this is another way of making this statement. So this is not a new relation that we are defining, but this is a different way of saying this. And also the meaning of this is, as we know, A is related to B or A equal to B. So basically combining these two statements into one, that is this, and the meaning of this is similar to the earlier case. So this is same as this statement. And as we are used to these notations, we'll use them freely without explaining this again. Okay, so this set of natural numbers, they're all non-negative. Okay. Now let's just go back to the successor function. So this was just this map, right? X going to x plus 1. So one trivial observation here is that if you have two reals, x and y, x less than y, then this comes from the first property of ordered field, right? X less than y, and you take a third element, then x plus that element less than y plus that element. And in fact, you can go in the opposite direction also. If you have x plus 1 less than y plus 1, you can take your third element now to be minus 1. So this plus this less than this plus this, which would give you the left hand side. So this is a two-way implication. Okay, the other observation which would be useful, which is again straightforward completely, but would be useful, is the following. You take s of x plus y, so that is x plus y plus 1, which is by commutativity, this is sx plus y, which is also x plus s of y. So you don't need to look at any special subset. This holds for all pairs of real numbers x and y. Okay. So all right, now we continue from here. So every element of n is non-negative, which means s of x is going to be, so if x is greater or equal to 0, x plus 1 is going to be greater or equal to 1, which is greater than 0. So that's another property that you immediately observe. Okay. Now, is it possible that this set n is bounded above? So when do we say set is bounded above? When it has an upper bound. Okay, it has an upper bound in the set of real numbers. So a subset there exists B bound of A. And what is an upper bound? I think upper bound I have to mention, right? So upper bound of A would mean, B is an upper bound of A would mean that for every A, either this or this. So one of the two holds. Okay, now is it possible that this set that we have defined, it is bounded above? So what happens if it is bounded above? Let's say B is an upper bound and N is consists of elements here. So assume B is an upper bound for N. Okay. Now, what do we know about N? We know one thing, that N is non-empty. The element 0 belongs to N. So it is a non-empty subset. Okay. Now you go back to the definition of the set of real numbers that we have taken. The last property that we had listed, the least upper bound property. What does it say?
Any subset of R, if it has an upper bound, then it will have a least upper bound.
Any non-empty subset of R
Yeah.
that has an upper bound has a least upper bound, right? So here you have a non-empty subset. So we are assuming this, and under this assumption, N will be a non-empty subset that has an upper bound. Okay, so by that property, this will admit a least upper bound. So then N has a least upper bound. Let's call it beta. Okay, what happens then? So if beta is a least upper bound, that tells you that anything smaller than beta, that's not going to be an upper bound. That is what is a least upper bound, right? So you take, then the following is true. If x is less than beta, then x is not an upper bound for N. Okay, now x is not an upper bound for N. Another way of saying that would be that there exists an element y from the set such that x less than y, right? So this part is same as this part. Okay. So for this least upper bound, we have this property that whenever you take something less than the least upper bound, less than beta, there would exist an element in the set which is bigger than that element. Now let us look at beta minus 1. Beta minus 1 we know is less than beta. This will follow from this fact, basically 0 less than 1, so minus 1 less than 0, so beta minus 1 less than beta, which means that there would exist a y here which comes from the set N. Okay, Now the set N is inductive. That means S of Y would also be in N. Since Y is in N, S of Y is also in N. But now you compare S of Y and beta. So Y is bigger than beta minus 1. Just I'll shift everything up and write down here. So beta minus 1 is less than Y. Then beta is less than Y plus 1, which is nothing but S of Y. So you have produced an element in N. N is inductive, so this Sy also must belong to N. You have produced an element of N which is bigger than this list upper bound, which is a contradiction because there cannot be anything bigger than an upper bound in the set. So that will give you a contradiction, which means that your initial assumption that you are working with, that has to be wrong. So N is not bounded above. Okay. And here you will see the advantage of defining N this way. I mean, suppose it, okay, this you, I mean, try for yourself. Suppose you try to define N where like 1, 1 plus 1, 1 plus 1 plus 1. So you try to somehow make that a little bit more, a little bit clearer, and say you take that as definition, and then try and prove this statement. Like a precise proof, rigorous proof, where you supply every step of the argument. Then you will see that you will have problem at some stage. Whereas here, if you just break up the proof, you'll see that we have not used anything other than the defining properties of R and statements that we have derived along the way.
Sir,
Yes.
so these defining properties, don't they allow us to conclude that X is less than S of X?
X is less than
S of
S.
X.
Yes, of course, because X
So-
and S of X is X plus 1, right?
Yes. So
So
can't we
this would follow from the first property of ordered field.
So can't we use that? Suppose B is an upper bound.
Huh.
Then since N is inductive, S of B is also in N.
No, but B need not be from N.
Okay. Okay.
Upper bound need not be from the set itself.
Okay, sir.
Okay. So
Yeah.
that you can see, for example, if you take a subset of the form, let's say this in R. Okay. This is something that is bounded above. This will have upper bounds in R. Okay. For example, 2 would be an upper bound, 1 would be an upper bound. But you won't get an upper bound for this set from this set. Right. So there can be subsets which are bounded above, but they don't have any upper bound from within the set.
Okay, sir. Yeah.
Okay. So next we come to another property which is going to be important. So let's say you take two elements in N. Then okay, I'll keep it separate. So then x is less than strictly less than y if and only if there is another element from n such that okay. So this is a property special to this set. This is not true in general for two real numbers. For example, if you take a real number and if you take this, right? So you can construct, okay, this on, I mean, you have to specify a subset. So maybe I won't mention this. You can have other subsets for which this is not true. But n has this property that when two elements of n, there will be strict inequality between the two. If and only if this happens. There is a third element such that when you add ace of something to the smaller one, you get the bigger one. Or you get, when you add ace of something to one element, you get the other one. Then x is less than y. Okay. Now, so if and only if means there are two implications here. Now, let's look at the second one first, second implication. In other words, we are taking two elements from n and a is another element, and you assume that so do they imply x less than y? So from whatever we have done till now, can we conclude this? We have seen something about s of x for x belonging to n, right? Here. So for any element in n, s of x is strictly greater than 0. In general, every element of n is greater than or equal to 0. But if you take image under s of x, that has to be strictly positive. So now use that. Just a moment. Yeah. Actually, I forgot and I did not see the chat message. So during the lecture, you just interrupt me and tell me, because I don't look at the window so much. I forgot to share the link. Sorry. Here it is. Okay. So this we know for all x belonging to n. So these together with these two together will tell you that okay, maybe I should not use x here. So here I'll use it for the element a. Same statement, but just so that notationally we are fine. So SA is positive and x plus s of a is y. Those two together will tell you that x is less than y, right? because also observe that what does it what is the meaning of this, or what is another equivalent way of saying this? It's same as saying that, right? So if you use that, so these two are equivalent statements, different ways of saying the same thing. So now you can see it immediately. So you this should happen whenever you have 0 less than y minus x. Now y minus x is, by your assumption, is s of a, and s of a you know is positive. So you are done. So one direction here in this implication, that is fine. You don't have to worry too much about this. And the other direction. So the other direction is the following, that xy belongs to n, then x less than y implies there exists an element such that x plus sa is y. Okay. Now the way we'll prove this is the following. So we want to show that this happens for every pair of elements in n. Okay. So let's form a subset of n as follows. You collect together all those points of n for which this statement holds for every y. So here is the condition for every y in n, x less than y implies there is a, so this is the exact same statement. So this is your set J. So this is just a subset of n, the way you have defined it. So you're taking each element of n, then you are verifying whether this condition holds for that element x. If this is true, you include it in your set. If it doesn't, then you don't. Okay. So the first, so now the idea of the proof is to do the following, to show that 0 belongs to J and J is inductive. Now, once you show these two things, it will follow that. What can we say from that?
N is a subset of J.
N is a subset of J, which together with this, the fact that you have started with a subset of N in the first place, the two together will tell you that N equal to J. J has to be the entire N. Okay. So let's see if these two assertions are true. So 0. Does this hold for 0? So what do we need to check? We are now verifying this statement, whether this is true. So what we need to check is, whenever 0 less than y, y is something in n, does this imply that there is an a in n such that 0 plus s of a, 0 plus s of a, which is s of a itself, is y. So this is exactly this statement, right? I have just expanded it, written it out in detail. So this is something that we need to check. Okay. So this will follow from the following property. That n is in fact union of these two. Okay, so basically we try to prove both these inclusions separately and use definition of n and whatever has been done till now. So for example, you try to, so this right hand side definitely contains 0, the way it has been defined. You try to show that this is inductive, the right hand side, then you will get this inclusion. It's an inductive set containing 0, so n would be contained in that, and so on. And the right hand side is contained in the left hand side. For that, that would be in fact even easier. So you try to write down a complete proof of this statement. Okay. Now, once you prove this statement, now you look at what we are supposed to show just now, supposed to verify. So we have something in n which is greater than 0, which means in particular this is different from 0. So this y has to come from this part, right? If you have an element here in n which is not this, then it has to come from this part. So that would tell you that there is in fact something in n such that, which is what you wanted to check. So you will have this part once you write down a proof of this statement. Okay. Now the second one, J is inductive. So what do we need to do for this to show that J is inductive? We have to start with something in J. Okay. And show that S of x, which is x plus 1, is in J. Okay. Now, starting with x belonging to J, this means that for every y in n, x less than y implies there is an A such that x plus SA is y. So that is essentially the meaning of this. This is equivalent to this statement, x belongs to J. And now we have to show this. Now, what is the corresponding statement here? That for every z in n, x plus 1 less than z would imply there exists B such that x plus 1 plus s of b is equal to z. So now you check whether you can derive this from this property, this one from this. So our job is to start with a z such that this happens, right? And then try and show that there is a b for which you have this.
So we can say that suppose there is a z that this happens, then we can say that since x plus 1 is less than z, that x is less than z minus 1.
Right. Okay, so let me do the following. I'll just write down what you just said before. I'll just copy and paste this on the next page, and then right now, yeah. Now go ahead. I'll write down what you're saying.
Yeah, so let for any z belonging to n such that x plus 1 is less than z.
So this is where we are starting, right?
Yeah.
So this means that x is less than
Z
z
minus.
minus. Okay.
So since z belongs to n, then z minus 1 also belongs to n.
Why? Why is that?
Because z is greater than x plus 1, which means z is not equal to 0.
Z is
Equal to 0
greater
which
than x plus 1. So which is
greater than x, which is greater than
greater than equal to 1, which is greater than 0.
Yeah.
So z is
Greater.
greater than 0. Z comes from n. So
Z belongs to n, which means that there exists an A such that.
okay, so this is a statement that you are using here, right?
Yes. Yes.
Okay, so maybe I'll just write down, because this is also a statement that, okay, it would follow, but one needs to give a proof. Okay, so let's go ahead, assuming this now.
Yeah. So then, since the above for z minus 1 is true, there exists A in n such that x plus sa is equal to z minus 1.
Right. So now we are going to use this, which we know, where y is z minus 1. So what we are going to get from this statement is that there is an n, a belonging to n, such that x plus s of a is z minus 1. So
Yeah. Then we add 1 to both sides. And I think that's the proof.
right. So you have, in fact, your b is going to be the same as a now for this choice of a.
Yes.
Okay. So that shows that J is inductive. So now we have both these, which means that n is contained in J, but we started with a J which was a subset of n to begin with. So you have J equal to n. And that means that another way of saying, I mean, the conclusion from that is J was the set of all those x's for which that statement holds. So for every x in n and for every y in n, x less than y implies there is an a such that x plus SA is y. So that takes us back to the original statement that we wanted to prove. Okay. So basically what it tells you is that for elements in n, you will have strict inequality if and only if they differ by something in the image of S, something here, right? Okay. One consequence of this would be that uh, if x and y are in n and x less than y, then maybe I'll keep this separate.
So are you
X
right?
is,
Because it's not showing.
oh, okay, sorry. Now you can see it has updated, I think.
Yes.
Yes, sir.
Yeah, okay. Right. So corollary would be the following: you take x and y belonging to n, then whenever x is less than y, then Sx is going to be less than or equal to y. This is because whenever you have this, now we know that y is equal to x plus s of something. And that something, s of something means that something has to come from n also. Okay. Now, this is something we have observed, and I mean, it's straightforward that x plus s of a is same as s of x plus a, because it's x plus a plus 1, the left hand side. So y is equal to s of x plus a comes from n, which will give you this inequality. That is either because every element of n is greater or equal to 0, so you'll get this. And again, the implication goes in the other direction also. So this is going to be a corollary of the earlier statement that proved. Okay, so the two exercises here you should do. One is that you take any element in n. Okay, so A and SA, these are, I mean, SA is greater than A, that we know. Now you look at this subset of R. This will not have any element from n. This is going to be empty. And another exercise. You take an element X in R, which is bigger than -1, then this intersection N is a singleton. Okay. Now, next comes one important property of the set of natural numbers. Suppose you take a subset non-empty subset. Smallest element. So what is a smallest element, largest element? So smallest element of set A. Smallest element is exactly what you know it to be, right? An element of the set A which is less than or equal to everything else in that set. So basically a lower bound which comes from the set itself. So A naught is the smallest element if A naught less than A, sorry, or A naught equal to A for every A. Okay. And similarly, largest element is similar, but on the other side. So largest element, it's an upper bound which comes from the set itself. So B naught is the largest element if okay. And in general, for non-empty subsets of R, we know examples where they don't have any smallest element. Let's say this subset. This does not have a smallest element, and that we can prove, right? Because any element here is strictly bigger than A, and this cannot be the smallest element because we have seen this. So this would be something which is in this set again, which is smaller than this. So this does not have a smallest element. So that is a property special to so subsets of N has this special property. Okay, right, but we have to prove this statement. So this is the statement that we want to prove. So the proof, sorry, I'm just going to the next page, is it? So how to go about proving this statement that any non-empty subset of this has a smallest element. Okay, I'll just outline the proof. So the statement that you want to prove is that for every non-empty subset A of n, subset A of n, A has a smallest element. Okay, so let's assume that this is not true. So what is the negation of this statement?
There exists a subset of n for which there is no smallest element.
Right. So there is a non-empty subset A of n such that A has no smallest element. Okay. Now you form this set A. L is for lower bound. So all those reals for which X is a lower bound for A. Okay, A is a subset of n. N is contained in this. This is something we already know. So there are lower bounds. In particular, anything less than 0 would be a lower bound. 0 itself would be a lower bound. So this set is going to be non-empty. This set is going to be non-empty. This set is going to contain 0. 0 is going to be a lower bound. Okay. Now show that this set is going to be an inductive set. Why will it be inductive?
Because of the negation.
Because of the negation of
So we have assumed that there is no smallest element. Then for all elements of A, there will be an element which is smaller
so let's
than
say
A.
X is in AL. Okay. Yeah, go ahead.
So for all elements a in small a in set A, there exists a y in set A such that y is less than a.
Just
And
repeat again. Sorry. For every element.
small a in set A, there exists y in A such that y is less than a. And we know that x is a lower bound. I think somewhere from here we can pull.
How? Okay. Okay. Let me just do one thing. Instead of taking lower bounds from the set of all real numbers, let's restrict this a little bit. Let's take lower bounds coming from the set of natural numbers and see if it helps. So even then, this is going to be non-empty because 0 is going to be in this set AL. Okay.
But sir, if we take A to be 0, if we take A to be 0, 1, and 2, and then how can, I mean, 0 can be a lower bound for A, but how can 1 be a lower bound for this set?
No, I did not say 1 is a lower bound.
I mean, we have to show that x plus 1 is also a lower
Right.
bound.
But that is under the assumption that there is a subset which does not have a smallest element.
Okay.
Right. So the idea is to arrive at a contradiction, precisely. That's it.
So can we say that suppose AL is not inductive, then we have an x in AL which is a lower bound, but x plus 1 is not a lower bound. And if x plus 1 is not a lower bound, it means that there is some y in A such that y is less than x plus 1. But y is not the smallest element because it has no smallest element. So then there will be another
yes.
So there'll be another element which is even less than y. That.
So basically, you will then try to argue that the one which is smaller has to be smaller by 1.
Yeah.
And then you will say that this is less than y, so you are getting a contradiction, right?
Yeah.
So the point here is that, yeah, exactly. So the point here is within n, whenever something is less than something, they differ by at least 1. That is the thing you are trying to use.
Yes, sir.
Yes. And that is exactly the statement. Let me just go back a little bit. That is exactly this statement. If you think about it, when you take two elements within n, okay, they have to differ by s of something, which is at least 1.
Yes, sir.
Right. So that is the thing. That is the statement that that is the property that we are trying to make use of. So, okay, so maybe you can try to write down the argument, what you are trying to give now. Just take your time and try to write down the argument, and then like maybe on the course page you can write down the argument, and then we can see. So the idea is correct, you just have to execute it. Okay, so that is essentially the proof here. So whichever way you go about writing it, that is the idea, and that is exactly why I just modified the description of this set. So when you restrict yourself to the set of naturals, two elements should differ if they differ by something, at least one. So S of something, which would give you that. Okay, maybe I'll leave this part. So, but one thing you have to do, you have to participate. Like on the course page, you have to write down the argument, because I mean that is why I'm omitting now. So you spend a little time, write down there. It's okay if there are some small mistakes here and there, but do try to complete it. And if you go in the directly from the definition of an inductive set, again it would use the same property. So you start with X belonging to AL, then you try to show that, so then you will be trying to show that X plus 1 belongs to AL. So this will mean that X is a natural number, X is a lower bound. Now make use of the fact that A does not have a smallest element. So here, even though it is less than equal to by definition, you will actually have strict inequality. Now you use the fact that in such a case, you have to have X plus S of something equal to A. And then you come up with a like this, you can write as S of X plus whatever it was there. Let's call it B equal to A. So this should be less than equal to A. So this would be a lower bound. So again, the same thing. So you can try to complete the argument along this line also. Either way, it's okay, but do write down, do make use of that discussion page a little bit more. Okay. So such a set is called an well-ordered set. What do I mean by that? Set is called well-ordered if every non-empty subset has a smallest element. Okay, so this is a definition. So what we have just now shown is that N is well ordered. Okay, now we give an exercise here. Suppose you have a set A, subset A of N. A is bounded above, then A has a largest element. So you can either try to prove it directly by using similar properties or whatever, or another way would be now that we have shown that n is well ordered, try to reduce it to a statement about n being well ordered. So from out of A, you construct another subset such that largest element of A would correspond to a smallest element of that set, and then you infer that A has a largest element from the fact that that set has a smallest element. So that would be one way to argue. Okay. So now let's look at some of the consequences, some of the properties that we have derived along the way. So one thing we have seen is that n is not bounded above, that we saw at the start today. So one corollary of that would be the following. So suppose you take a positive real x. So take a real x which is positive, then there exists an element, there will exist a natural number such that, okay, so this is something that we know, but now you see that this would follow from these properties that we have proved. So 0x. So this is the statement that there would exist an n such that 1 over n sits between these two. And why is that? The reason is simple. So you just rewrite this. So this is equivalent to saying that 1 over x, you're dealing with positive numbers here. So in particular, non-zero. So taking inverses, multiplicative inverses is fine. So this inequality is same as this inequality. So what you are essentially saying is that given this number x positive, there is a natural number which is bigger than this number. But this is exactly saying that n does not have an upper bound, right? Because if there was no such n, then every element in this set would have been on this side of this number, and this would have become an upper bound, which cannot happen. So that's why you'll be able to find something in n which is bigger than this, which is same as this inequality. Okay. Then another property. So let x and y are two reals, x less than y. So m and n from n, but n non-zero, such that m by n. So this means basically m into 1 over n, right? Such that so earlier, you recall what we had proved was that given any two reals, x less than y, we can find another real. And now this statement is a little bit stronger. Given x and y, x less than y, there is a number of this special form in between them. Okay, so fine. Let me just at this juncture, let me give this definition. So elements of n are that we have already used this term, natural numbers. Okay. Integers, the set of integers will denote by z, and this is n union minus n. So minus n, this is no notation. So it means just this set. So n together with negatives of elements of n together, you call them integers. Okay. Rationals, what are rationals? Where m so these are called rationals that we know. Just officially giving the definition, that's all. Okay, and in fact, this set is same as so you can allow n also to come from z. Okay, so what this statement on the left side says that given any two reals, there is a rational in between them. Okay, so first, just to make things a little simpler, if x is less than 0 and y is greater than 0, so 0 sits in between, then there's almost nothing to do, right? This is going to be a rational which sits between the two. So you're done. So this case is trivial. Now let's look at this case. Now in this case, what you can do is you can look at minus y and minus s instead. So then you would have reduced it to the case this. So what I'm trying to say is it's enough to give a proof for this case. Then all other cases you can derive. Like this case is in any case, this case is trivial. No matter what x and y are, if one is less than 0, one is bigger, 0 is there in between. If both are negatives, you look at their negatives minus x and minus y, and you reduce it to this case. So If m by n sits between the two, minus m by n would sit between these two. So it is enough to give a proof for this case. Okay. So what we are trying to show it that is this, that there exists so how do you prove this? So let's just try something. Let's fix n equal to 1 and see what can happen. So let's say this is the number 1, which is 1 by 1. Then what is, so here m equal to 1. So the next one with denominator 1 is going to be, okay, so the way I have drawn the picture, maybe that would be bigger than y. So 1 is less than x, but 2 is bigger than y. You are jumping over the interval x to y and reaching the other side. But maybe if you take a big enough n, then this cannot happen. So let's say you have taken 1 by 5. Now you look at 1 by 5, 2 by 5, etc. Okay, 3 by 5, etc., etc. So at some stage you will be close to x, and then so in order that you don't jump over the whole interval and land on the other side, you will need some restriction on 1 over n, right? So what will that be? If this length is small enough, then you cannot jump from one side of the interval to the other side. So what will that restriction be on the length 1 over n?
Less than y minus x.
Exactly. So this has to be less than this. Now you go back to an earlier statement that we have proved. We, given this number, which is positive, we in fact have a natural number such that this would happen, right? This is guaranteed because n is not bounded above. This is something we have seen today. So first you get an n such that 1 over n is less than y minus x. So this is, just go back to the page where we proved this. Yes, it is here. Right. So you choose such an n. Okay. Now, next task is to identify this this number. So for that, we do the following. We take k belonging to n such that k over n is less than the smaller of the two. Okay. Okay, I should not say this is not fair, but basically you're looking at all those cases for which k over n is less than n. So 1, 2, 3. So up starting from 0 up to some stage, things would belong here. So we are looking at this set, this subset of n. Now this inequality, now n is fixed, right? N is something that we have chosen. So n is now fixed. N we have chosen so that this happens. So you choose one such n, fix it. Now, for this fixed n, we are looking at this set A. Okay, now what is this inequality? This inequality, another way of writing this inequality would be that k is less than n times x. Okay, so we are looking at all those natural numbers for which are less than n times x. So this is bounded above, right? So this is a subset of n which is bounded above, which means that it has a maximum element. So this has a maximum element and call it m. Which means that m by n is less than x, but m plus 1 by n is not less than x, because then if it was less, then m plus 1 would also belong to this set, and then m will not be the maximum element anymore. So m plus 1 is on the other side of x. Okay. Now m plus 1 by n minus x, this distance is less than m plus 1 by n minus m by n. Okay, this you can derive using basic properties like a less than b, c is a third element, so a plus c less than b plus c, that property. Okay, but this is 1 over n. And 1 over n we know is less than, the way we have chosen our n, y minus x. So the inequality that you are getting is, so this distance is less than this distance, y minus x. And from this you conclude that m plus 1 by n is less than y. So in fact, this number lies between x and y. So you have produced a rational number between these two reals, x and y.
Sir, this need not be true.
Which need not be true?
Because we have said that m plus 1 by n is not less than x. So it is possible that x is equal to m plus 1 by n.
Okay, yes, you're right. So how can we circumvent that? Yes,
Then we have
absolutely
to
right.
take m plus 2 by n to be the
Uh,
between them.
Redefine A
yes,
with
I think
weakened point.
that would be the easiest. So here
Yeah.
you make this modification, correct? Because all we can say here, I mean, going by the earlier definition, is that m plus 1 by n will not be less than x, but equality is not excluded. Yes, so that if you modify it this way, everything would be taken care of. So earlier definition, this was the problem, that m plus 1 by n need not be strictly bigger than x, but now it would be, right? So in that part of the argument, there was a mistake. M plus 1 by n could have been equal to x, and still m could have been the maximum of that set that I had defined earlier. So that would be avoided if we redefine it this way. Okay. So I think we have a few things left, which okay. The set of rationals we will denote by this symbol q, right? So show that this I had mentioned while defining the set of real numbers, that first 4 conditions is what you need to check. This is a field. Again, this means while defining the set of reals, we had these first 4 conditions, then another bunch of 4 conditions, and then the third condition which connected the 2 operations. So those 3 sets of conditions are the defining conditions of a field. So just verify that for this set of rationals, along with these 2 operations, that gives you a field. It satisfies those conditions. So you have to verify that these are operations on Q, so you don't get out of Q when you perform these operations. That's number one. And then those properties would, after that, those properties would basically follow from the corresponding properties of the bigger set, the set of reals. 3, this together with the order relation is an ordered field. Okay. So in fact, when you look at this relation on Q restricted to Q, it gives you an ordered field. So it in fact satisfies the first 4 conditions. So except the last condition, it satisfies everything in the definition of R. Okay. Okay, this is something that you can try, but maybe we'll spend a little time next time on this, or maybe I'll write something on the discussion page. So this is where it differs from the set of real. So this is going to tell you that this is strictly contained in R. So this is not going to give you the entire R, because R satisfies the last condition, least upper bound property as well. But this Q, this subset of R that you have described in terms of the natural numbers and then the integers, this is not going to have this least upper bound property. So even though it's an ordered field, it will not be the entire R. There will be elements outside this in R. So basically this is existence of numbers which are not rational, existence of irrationals. So either I'll spend a bit of time next time at the beginning, or if I get time, I may write on the discussion page also. Okay, so I'll stop here today. Any questions? Directly related to what we are doing, or anything else? Just feel free to ask. Okay, so if not, then let me end the session. So we'll see you next week.